fact, I just bumped into somebody in the hallway earlier, and we ended up talking about it, and he had a very different perspective on the whole talk than I did. That just happens because we had a collective experience and we're walking around.
Okay, good morning, everybody. I'm here to talk about functional programming. So the obligatory beginning, like what is functional programming? Out of curiosity, how many people are here without knowing what functional programming is? Okay, a couple of people, okay, good. So functional programming, so what we are familiar with is imperative programming. In imperative programming, you specify instructions that manipulate some state in order to achieve a goal. Right? This is what we do in C++. We've got a whole bunch of variables, and then we have statements that modify those variables in some way. And eventually, we will compute a result. This is also the way the CPU works, right? We have memory, we manipulate those memory using assembly instructions, and in the end, we will have different values in our memory, and that's the output. And this also how something like an IKEA manual works, like a sequence of steps in order to assemble your furniture. Contrast to that is declarative programming. So in declarative program, you only specify the desired outcome, and then some system figures out how to achieve it. Right? And this is the case in like functional programming like Haskell and logical programming language like Prolog. But also if you have a formal grammar. Right? So in a grammar, you just specify what syntax is valid, and you don't specify how to parse it. Right? There are like separate algorithms that then parse your formal grammar, but this is not part of your specification. Or the thermostat in your room. Yeah? You just set the temperature you want, and then the system figures out how to achieve the temperature by cooling or heating as necessary. Right? You don't directly control whether to heat or cool, like you just specify the goal, and then the system figures it out. And now functional programming is a form of declarative programming where you compose functions. So this is the only slide that's going to contain Haskell, no, don't worry. This is like a very classic example, like we've got the mathematical function faculty written in Haskell. It takes an int and returns an int, and we say that the faculty of 0 is 1, and the faculty of n is n times the faculty of n minus 1. Right? And these are just rules you need in order to compute the faculty, but it doesn't describe how to compute it. Right? In C++, we would probably write some sort of loop that iterates over n and then multiplies it with itself, but here we just specify the mathematical definition, and then the system figures out how to compute it. Here's quicksort in Haskell. So it takes a list of integers and returns a list of integers. And we say that the empty list is already sorted. So the empty list sorted is the empty list. And then if you have a list that contains one element followed by some others, we pick the first element as our pivot, get all the elements that are less than the pivot, concatenate that to the pivot, and get all the elements that are greater than the pivot. And this where clause here, this doesn't define like any temporal relationship in which order to compute it, right? It's just the definition of left and right. This is a very declarative way where we compose our functions together in order to compute the list. We don't specify any sort of instructions in how to compute it. Now, why do we want to use functional programming? Well, the big benefit of functional programming is that you don't have any state. This makes it easier to reason about because you don't have to keep all your variables in your head. This also makes it easier to parallelize, right? If you don't have any state, you don't have any shared state, and so you can just run all your programs in parallel without having to worry about race conditions. So functional programming, especially like in modern times, is really important. So why would you not use functional programming? Well, it's fundamentally less efficient. This is because we're programming CPUs, and CPUs are imperative, so there is some overhead in order to map the declarative thing to the imperative thing, right? C++ allows us to directly model the way the hardware works, whereas in functional programming, we abstract it, so we are less efficient. But this is a talk about functional programming in C++. And C++ isn't a pure functional language, right? We're not forced to use functional programming, right? This means that we can sort of take the best of both worlds. And to take the best of both worlds, the key is one word in this definition. Functional programming is declarative programming by composing functions. And composition is the key, because functional programming is all about compositions. You take existing pieces and you compose them together. And so in C++, because we only have like the majority of the performance is in like some functions, right? And we can write those fundamental building blocks using very efficient, imperative, well-tested, optimized C++ code, and then we can compose them together using functional programming. And so on the high-level composition, you don't have to worry about any state. All the state is hidden away in the building blocks, and the building blocks are really efficient. and like the composition isn't what's gonna slow down your program, right? So that way you get the best of both worlds. And throughout this talk, we will gonna look at various places on how we compose functions in C++ in order to get this paradigm. So let's begin with the biggest thing, algorithms, right? Composing algorithms. I've brought some like leak code problems, slightly modified for like pedagogical effects, and we're just gonna go through them. So the first one, our input is a non-empty list of integers, and what we want is the biggest magnitude of an odd integer in the list. What I mean by that, if that is our input, then the output is 7, because -7 is the odd number with the biggest magnitude, right? And this is how we would write it in imperative code, right? We've got a range. We remember the current candidate. We loop over all elements, compute the magnitude of the element. If it's odd and bigger than our candidate, we update the candidate, and in the result, we return the candidate, right? This is imperative programming. We specify the instructions on how to compute the thing with like a whole bunch of intermediate state. So let's think about it in terms of composition. So what is the actual composition? What are the fundamental building blocks we're doing? Well, one composition is we need the magnitude of every number in our range. Then we need to filter out every even numbers and keep only the odd ones. And in the end, we will find the maximum. So splitting this up into those three things, the code can look something like this. So the first step is we compute the magnitude of each number using std transform. Right? We give it our input range and append that to a vector and compute the absolute value of each one in turn. And then in the second step, we filter out the even numbers and keep only the odd ones. Right? So we use copyIf and copy only numbers that are odd into a new vector. Right? And then finally, we can call max to get the maximum value. Now, as an aside, the stdr here is the std ranges namespace. So since C++20, we've got much more convenient algorithms where you don't have to specify the iterator pairs, right? You can just write the container or range directly and some more goodies. So like just replace your code using std ranges instead of std, and you will have much fancier algorithms. And just for like slide purposes, I've abbreviated std ranges to stdr. Now the code we have with the algorithms works, but it's like not very efficient, right? Because we're doing eager composition. We're creating all these intermediate containers, which require memory, which are expensive. We also eagerly compute all intermediate results, even if unneeded. This isn't a big problem here, because we actually need all the values in order to find the maximum. But like in general, we might do more work than necessary. And then we still have state, right? We've got all these intermediate containers, and we have to keep them in check. So the solution to those problems is to use lazy composition. And for that, we can use views. They are also added in C++20 as part of the new algorithms, and a view is essentially a lazy range. It's something that computes values on demand. So when you create a view or compose views, this actually does nothing yet, right? It just describes some sort of pipeline. And only when you start iterating do you actually do things, right? So only when you pass a pipeline to an algorithm or to a loop, you will compute each value of the pipeline in order as you go over it. So it doesn't do any unnecessary work. And this allows us to truly use the functional pipeline style where we don't have any intermediate state. So with views, our example can look like this. So the first step, we compute the magnitude of each number. And for that, we pipe the range into std transform. As before, so std view is the view. This does not eagerly compute in a range. Instead, it specifies that as you iterate over it, call this function on each element. So when we iterate over magnitudes, we will only get the magnitudes of the range by calling the function each time we iterate. Then we call filter to filter out even numbers, right? So iterating over the odd magnitude, this will skip all values that don't satisfy the predicate, right? So when you call begin, it will skip forward and find the first one that isn't odd, and then return that. And each time you increment, it will skip over towards the next one. And the value in turn comes from the previous range, so it will call the function to get the thing. And then we pass the entire thing to max. Before, like the first two lines, they don't actually do anything yet, right? We just compose pipelines. And only then in the loop, in the implementation of max, we have a loop that iterates over all the things and triggers the computation each time, skipping forward using the filter and so on, and computing the maximum. And now you might say, well, we still have states there, these intermediate variables, but that's not really state. That's just a named label for some part of the pipeline. So traditionally, you would probably write it like this, just inline the thing in the argument. We take our range, we compute the absolute values, and we filter them, and then we compute the maximum. And that way, you can see the fundamental composition, And compared to the imperative code, you don't have any variables you need to keep track, right? It's a lot less difficult to make bugs, right? For example, like in the previous thing, like the candidate we initialized to something, what if the range was empty, and then we would return the candidate, right? We don't need to worry about that. So this is the functional composition style. This is a back to basics talk, so I'm going to ask you if there are any questions before I continue. Yes?
Would it be faster to filter before you do the transform?
Would it be faster to filter before you do the transform? Probably, yes. In this case, it doesn't matter because like the oddness doesn't change before you do the transform, and then you skip the absolute. Yeah, probably good catch. Okay. So the takeaway here is that we've got the composition shape. You have a range, and you want a different range, right? Different values or different lengths or something. And for that, we can use, for example, transform. Transform takes a range and returns the range by applying a function to each element so that it manipulates the values. And you've seen filter, right? This only keeps elements of the range that satisfy a predicate. And then there are a couple more views like this, for example, take while and drop while. They like remove some prefix or suffix of the range based on a predicate, right? And those are like designed for like take a range, return a slightly different range. And then we've got the composition shape. We got a range and we want a value, right? And for that, we've got functions, right? For example, max and min returns you the maximum or minimum value. There are some variations that give you an iterator instead, if you want an iterator to the thing, and so on. Count is another one that takes a range and counts all elements that satisfy a predicate. We've got all of, any of, none of. They return if like all of, any of, or none of satisfy predicates. And then we've got like find, to like find a particular element or one that satisfies a predicate, and like search to like get a subrange that matches some other range. And those are used when you have a range and you want to get a particular value out of this. So let's look at another problem. So we want to compute the smallest Fibonacci number that is above a threshold. So we get some threshold x, and the output should be the smallest Fibonacci number, the greater than that. So for example, if our threshold is 9, then the answer would be 13, because the 6th Fibonacci number is 8, which is not yet bigger than our threshold, but the 7th Fibonacci is 13, which is bigger than our threshold. So that is the smallest Fibonacci number greater than 9. So I'm not going to show the imperative code again. Instead, just going to think about directly what is the composition. Well, we need to do two things here. First, we need all the Fibonacci numbers. And then we find the first one that is greater than x. So the second step is easy. If we have all our Fibonacci numbers, and then we call findIf to get the one that is bigger. Right? And because they are like assuming we generated them in like increasing order, findIf will give the first one that matches the predicate, which is then by definition the smallest one greater than nothing. Now, of course, there's a bit of a caveat. There are like infinitely many Fibonacci numbers. Right? So can we truly generate all Fibonacci numbers? And the answer is we don't need to, because remember, views are lazy. We only generate values on demand. So we can describe an infinite range, right? And as long as we only need finitely many elements, this is totally fine. So as findIf will iterate over the Fibonacci numbers, we will generate them one after the other. And as soon as we found one that matches the predicate, we will stop, return from the function, and don't compute anything else. So how do we get all the Fibonacci numbers? Well, one way trick we can do is we can use iota. Now, iota is a simple view that just generates increasing integers, beginning at the starting values, right? So iota of 0 generates you 0, 1, 2, 3, and so on, up to infinity, or rather until we have like integer overflow or something, right? But like conceptually, this is an infinite range of integers. And then we have our function fib that computes like the nth Fibonacci number, and we transform the integers, right? So this will apply the function to each integer, which will in turn expand to like fib0, fib1, fib2, fib3, and so on up until infinity. Then we pass that to findIf, and this will iterate over the Fibonacci numbers until we found one that is bigger than our threshold. This is like the definition of fib, right? If n is less than or equal to 1, then we return n, otherwise we sum of the two previous. And this is like an incredibly inefficient definition of fib, right? This has like exponential runtime complexity, but it has functional programming, right? Because we like compose functions. But this is one of the cases where we truly don't want that, right? We don't want functional programming here. This is like too slow. We want instead the imperative code where we've got the loop, right? I use iota to be fancy, so we loop over like n and then compute Fibonacci numbers and return it, right? This is still not the most efficient way. Like the most efficient way uses like matrix exponentiation, but I don't want to get into that. And of course, we have a problem here because like fib n like computes all previous Fibonacci numbers and then the next one, and we're calling it in a loop, right? So we're asking for like fib1, fib2, fib3, and each time we recompute all the previous one, right? This is not very efficient either. Like this has quadratic complexity. It would be a lot nicer if we could somehow say, hey, we just have one function that repeatedly computes the Fibonacci numbers, and we interrupt that in between to tell you, hey, we found the next Fibonacci number. And this is possible using like coroutines and generators. So a generator is essentially a way to write an infinite range yourself. And so here we just have an infinite loop that repeatedly like starts out giving you the first Fibonacci number, it then computes the next one, it results that, it computes the next one, and so on. And so like every time you call yield, you will return a value to the caller, but crucially, after that, the caller will jump back into the function and compute the next one. So when you iterate over a generator, you will start executing the function until you get the yield. This is the first value. And then when you increment the iterator, you will jump back into the function just after the yield. We have remembered all the previous state, right? Jump right back in there, compute the next one, and so on. And that way, we don't have like any like quadratic complexity here because we never recompute the previous Fibonacci numbers. Questions about this? Okay. And so what we've seen is a composition shape where we have nothing and we want to create a range. And for that, you can use, for example, iota if you just got simple integers, and like the pattern of iota and transform to something is incredibly powerful to just generate ranges. Then there's something like repeat. Repeat simply generates an infinite range that repeats the same value. And right this morning, I wrote some code that uses repeat. It's useful in some cases. And then if you want full control, you can use generators and co-yield to like create a custom range that contains the data you need. Okay. So look at the next problem. So we've got two lists of integers and a number x, and we want to find like one integer from the first list and one integer from the second list whose sum is x. So for example, if that was our list, and we want to find the sum 10, then the output would be the pair 2, 8, 2 from the first list, 8 from the second, and together they sum to 10. And again, what is the composition here? Right? We generate all the pairs, and then we find the one whose sum is x. And this can look something like this. So in the first line, we generate the Cartesian product. And the Cartesian product is just a range that contains pairs of all possible combinations of the two elements. Right? So if our list was like 1, 2, 3, 4, and the other one is 5, 6, 7, 8, right? Then we start out with 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, and then 2, 4, 2, 5, 2, 6, and so on. Right? So all possible products. And then we just find the one whose sum is equal to x, and return that as like the pair of two values. And this code works, it's perfectly fine. It's just incredibly ugly, right? Cartesian products, when you iterate over them, you get like tuples, like with one of each value. So in the find-if case, you have to like use get to extract the individual elements. And then we've got an iterator out of find-if, but we really want like the values, so we like turn the iterator back into like a tuple by using get again. Actually, I don't need the make tuple in there. It just star iter is enough in the last line. But like, it's a bit annoying. And like we at Thinkcell, we really like using ranges, and we really don't write like this ugly code. So we've got like custom range algorithms and can simplify that code. So we can just call our find-if. It's called find first if because it finds the first one. And there are two special features. So the first one is the lambda that we pass it. If the ranges are tuples, but the lambda takes multiple arguments, instead of a tuple, we will automatically expand the thing. So we just get the individual elements out of the tuple, A and B, and can write that more easily. And then the second thing is the return value or none. This allows us to like specify the return value of find. And in this case, we want like an optional value, and so we say return value or none, right? Similarly, we also have like return bool, return iterator, and so on. Like it's incredibly convenient. We've got like dozens of those combinations, and that way you don't have to manually wrangle the iterator. And so the composition shape here is, we've got like multiple ranges, and we want to create a single range out of those. And for that, for example, we have Cartesian product, and this is a tuple of all possible element combinations. There are like n times n elements for like two ranges, but remember, it's like generated lazily, right? So if you only generate as many as we actually need. Then we've got zip. Zip operates over the ranges in lockstep, and gives you a pair of corresponding elements. So the first element of zip is all first element of the subranges. Then the second element is all second elements of the subranges. And so it iterates over them in lockstep. This is also useful a surprisingly amount of time. Right? Especially a zip with sort of itself, and then you have a range, and then a different position in the range is very useful. And then in C++ 23 or 6 or something, we will have concat. Concat is just all ranges, all elements one after the other, right? So just concatenate all the ranges, and remember, this happens lazily. This doesn't do any allocation. It just iterates over the first one, and when that is done, it will start iterating over the next one, and so on and so forth. Okay, so another problem. We have a list of integers, and we want to find the length of the longest contiguous subsequence of increasing numbers. So if this is our list of integers, the output would be 4, because 2, 4, 5, 7 is the longest subsequence of numbers that are only increasing. And again, you probably know what's going. What is the composition here? We first split the list into like chunks of increasing numbers. Then we determine the size of each chunk, and then we return the maximum. In code, this looks like this. So we take a range, and then we pipe that into chunk by. Chunk by takes a binary predicate, and it will split it at the point where like 2 adjacent elements no longer satisfy the binary predicate. So the first chunk will start out with 1, and then it will call less on 1 and 3. Since 1 is less than 3, we will add 3 to the first chunk. Then our first chunk is 1 and 3, right? And then we check 2, 3, and 2, but 3 is not less than 2, so we split. So the first chunk is 1 and 3. Right? And then we continue on and add 2 to the next chunk, try to extend it as much as possible using the predicate, and split it when that's no longer possible. And so the result is a range of ranges. And remember, those are lazily generated. So when you call star for the first time, it will do the thing to find the end of the first chunk, and then return that subrange. And then when you increment the iterator, it will find the next chunk, right, and return that as a subrange. We don't actually care about the subranges, we just want their sizes. So we call transform on size, right? This calls size on each element in the range, which in turn is another range, so we end up with a range of the sizes of the subranges. And then we just want the max one, so we call that max, pipe that into max, and this returns us the longest increasing subsequence of integers. And like, if you were to write this just using like loops and so on, like, you'd probably put some bugs there in the initial thing because they're like tricky edge cases and so on. And using this sort of declarative style, you just compose the things. Once you like get in a mindset of trying to see the compositions there and know all your views and so on, it's a lot easier to write. So the composition shape here is we've got a range, and we want to return a range of ranges using, for example, chunk by, which splits it in a predicate. We've also got split, which just splits it when we have a particular value. Right? And then like adjacent or slide, which create like sliding windows in the range. So the first element is, for example, the first 3 elements, and then we've got the next 3 elements, and then the next 3, and so we've got like sliding windows. So whenever you need a sliding window, you can use adjacent or slide. Like one of them takes like the count, and the other one takes the count as a compile time size or something like that. That's the difference. Like one gives you a tuple, and one gives you a range. Okay. So I think the final problem I brought you is reverse words. So we've got a string, and we want a string where all the words, so sequences of letters are reversed, but the rest is in the same order. So for example, if the string is hello world exclamation mark, this is the output. Like we reversed all the words, but otherwise left them in the same order. And this is, I think, like a somewhat common like interview questions that's like really easy to solve by thinking about composition. So again, what is the composition here? We split the string into words. Then we reverse each of those chunks if it is a word, and then we put all the chunks back together. And so there's a lot of code, so let's go through this. So we start with our string, and then we split it based on words using chunk by again. In this case, the binary predicates takes the left and the right char, and if the alphaness differs, right, if one is a letter and the other one isn't, right, then that means we're at the border of a word and need to split the chunk, right? That way, we like aggregate all the words into one thing and then split it whenever we're no longer a word. And then we call transform on this, because we want to reverse the chunk if it's a word. Yeah. So the intermediate 2 in the predicate here eagerly creates a std string. This is because chunk and reverse of a chunk don't have the same type, right? So we need to have the same type to have them return from the lambda. This is why we do some intermediate string there. And then we're almost done. We now just have like a range of strings. But we actually want to like have a single string, so we call join. Join takes a range of ranges and flattens it, right? So it's a single range that contains all the characters instead of a range of strings, right? So if you have a vector of int, and you call join, you have a vector of int that is all the elements of a vector together. And then we convert that into a string. And then we're done with the result. And now if you're worried about the intermediate allocation there to create the strings, we were worried about that too at work. So we've implemented a conditional range. And this is essentially like a variant of two ranges that is still iteratable, right? So it creates like a variant of the two ranges, and then the iterator is a variant of the two iterators. And then it will iterate over whatever is the active one. And that way we get like the single type without having to do any dynamic allocations. I will see that I get that standardized in the future too, because it's like a really useful primitive. And so the final composition shape here was we have a range of ranges, and we want a single range. And for that, we can, for example, use join, which simply flattens it out back into a single range. You can also use join with, but adds a separator. So if you want some elements separated by commas, you can call join with, right? Join with of a vector with a comma creates a thing that, insert commas in between. So the general takeaways here are, you should try and identify like the small building blocks to solve your problems, right? And then match those to the algorithms, right? If you want to create ranges, use iota and generator. If you want to transform a range, use transform and filter. If you want to combine ranges, Cartesian product, zip, concat. Right? To split ranges, we can use split or chunk by. To join ranges, we can use join to put them back together. And then we need to know the algorithms for those, right? We've got all the various kinds of folds, which are called like minimum, maximum count, and so on. And then the various searches, like first and search. And with those tools, you can like solve a surprising amount of problems, right? In a very simple, very declarative way, just when you're talking about finding things. And so when we write this composition, as we can see, like we don't need for loops, right? Composing algorithms minimize the use of for loops because the for loops are in the building blocks and we don't need to write them ourselves. Okay. Questions about composing algorithms? Like this requires some composition, some intuition that you need to learn to practice. Yes?
Quick question. On some of your slides, I think like 37, for example, at the end you go from like a std view function to a std range algorithm. Do you know what's going on? Yeah. Std view join to std.
Yeah. So std view join is the result of this entire pipeline is like a very complicated range adapter. Like it's a join view of a transform view of a chunk view of a string or whatever, right? This is a really weird type. And we just want a string, right? So by calling to, we take our range and convert that into the specified container. So it will iterate over the range and like call pushback on a string to eagerly compute all the things, right? So at this point, we do an actual computation instead of having the thing that lazily computes the entire pipeline.
But then is new memory allocated only at that point that you call the std range?
Yes. So memory is only allocated every time you call to, right? And this does an eager computation. All the other things just describe a pipeline. And when you call to, you start running the pipeline just before when we pass it to algorithms.
Okay, thanks.
Yes?
Can you talk about a bit the time complexity of these algorithms?
Yeah, so the vast majority of like the views are linear because they just modify the thing as you iterate over them, right? There are a couple more that, like, for example, Cartesian product is actually quadratic because it simply needs to compute quadratically many elements, but the vast of them are like linear. Right? And then, I mean, of course, like here we've got like quadratic because we have a linear thing in a linear thing, right, to reverse the things, but like it's usually linear. Yeah. Okay. Yes?
Very good question. So I'm trying to understand why one would use views and ranges over things like just a for loop. I understand that it's basically the for loop done for you.
Yes. You'd hope so, yeah. So like, for example, like filter is just a for loop with an if, right? But the benefit of doing it declaratively is that you can take this entire pipeline and pass that to a parallelized algorithm, right? And then you've got like parallel for loops, like in a very trivial way, right? If you just did it by hand, you have to do more work. Okay, I'm gonna cut it here because I have like more slides. We can talk more about it at the end. Okay, so this was algorithm. Let's look at composing functions in general. So let's say we have this function. We have a user ID, and we want to unsubscribe that user from our mailing list. So we look up the user, we get its email, and we call remove on the subscriber list. We have some composition here, right? We start with a user ID, then we get the user, then we get the email, and then we do something with it. And so we've composed functions. Like this is a functional way of compiling code. We compose functions without any intermediate state. Now, of course, the problem here is like, what if the intermediate functions can fail? Right? So, for example, what if a user A might not necessarily exist, right? So when we look up the user, we get an optional user. And an optional user, like an optional T, either holds a T or is empty, right? So if the user ID is invalid, then we get nothing back, right? And then we don't have any user, then we also don't have any emails, right? So we need to handle that, right? So when we look up the user, only if we have a user do we have an email, and then we remove it. And we're still doing some sort of composition here, it's just hidden away, right? So we start with a user ID, and then we get a user or nothing, and then like the nothingness propagates through, so then we also have an email or nothing, right? And we only want to execute an action when we actually have an email. But like this isn't like clearly expressed in the code, right? This composition chain. So the question is like, we have an optional user. What we really want is like an optional email, right? Because we have a user nothing, and we want to map that to an email or nothing. And well, we can do this, right? If we have a user, we get the email, have to map it back into an optional. Otherwise, we keep an empty thing, right? And now we like have like turn the optional user into an optional email. And because this is incredibly common, there is a member functional option for that, transform, right? Because we're doing a transformation on the optional. Now transform takes a function, so optional T, transform takes a function that takes a T and returns a U. And then if we have a value, we invoke the function on our value, wrap the result in an optional, otherwise we're empty. And this allows us to turn an optional T into an optional U using the specified function that converts a T to a U. And now we can just say email, user.transform, get me the email. And this turns an optional user into an optional email by accessing the email member. So now we have an optional email. And now we want to only invoke the remove on the subscriber list if we have an email. And for that, we can use an if statement, right? So if you have an email, remove the subscriber from the user. But we can also use transform. So we sort of transform the optional email into an action. Right? So the function now has a side effect, and by calling it, we're removing the thing, but we're only calling it if we have a value. Now this doesn't compile because the result would be an optional void, right? Since the function returns void, and that isn't a thing, so we'd have to like return monostate, and monostate is like it's like void, but it's not void. Right? And this is a bit unorthodox, but we'll see how it's useful later. And now we can actually write our composition. So we start up by looking up the user, then we're getting the email, and then we're getting the action. Right? And like the first step can fail, and then we simply don't execute the entire pipeline. Right? So then we like declaratively specify the pipeline, and this will then execute. Now this pattern is like really useful if, for example, users might not necessarily have emails. Right? So now we might not necessarily have a user, and we also might not have an email. Right? And then we would need two if statements. Right? One to check whether we have a user, and then one to check whether that user has an email, and only then do we do the thing. Right? And dealing with optionals is like incredibly annoying, but we could imagine writing a function that sort of flattens them. Right? And just like the one for flattening ranges, let's call this join. This talk is a bit repetitive, this has a point. So we call join, which turns an optional into an optional T by just doing one level of dereference. And this sort of merges the two failure cases together, right? So afterwards, we can no longer distinguish whether we didn't have a user or whether that user didn't have an email. But when we don't care about that, this is useful, right? Now we can write join of the transform and get an optional email. But of course, this is a bit clunky. Like the better way is to simply not wrap the result in an optional, right? If transform didn't put the optional around it, this would be more useful. And there is a variant of transform that does it. It's called and then. It's similar to transform, but the difference is that the function for and then itself returns an optional U. So transform takes a T into a U, and then takes a T into an optional U. And because the function itself returns an optional U, we don't need to wrap the thing into the optional, right? Because this would just create the nested wrapping, which we don't want. So if we just call and then instead of transform, then we just have an optional email, instead of an optional email, because we flattened the thing together. And now we can put the entire thing back in our pipeline and say we look up the user, and then we look up the email, and then we do our action. And now we've got like two failure points in our pipeline. The lookup user can return nothing, or the user email can return nothing. And in either case, we will not invoke the final transform because our optional is empty. Right? And it's also clearly marked which sort of places in our pipeline can fail. Like only the ones marked with and then. Like the final transform cannot fail because it's doesn't use and then. And this is a very like functional style way of like composing multiple options together. Whether that's like actually better than writing the code with if statements is like up to your taste, right? Here there is no obvious like parallelization benefit, right? But it's possible to write it. Now, a user can have multiple email addresses, let's say, right? So a user actually contains a vector of emails. And then when we call the transform, we get an optional vector. And then we need an if and a for loop. And again, this is a bit clunky, right? Because we don't really want an optional vector, we just want a vector. And that vector should be empty, right, if you didn't have a user. Right? Luckily, this is going to be really easy in C++26. Because in C++26, optional t is actually a range. Right? It's a range of 0 or 1 element. Either we have a t or we have nothing. Right? So we can actually start iterating our optionals, which means that we can apply the entire range algorithms. So we call lookup user and transform to get our optional vector of emails. And then we want to have a single range, so we join it. Right? This flattens a range of ranges. Because an optional is a range of 0 or 1, right? So it's a range of range. And by joining it, we either get like an empty range, if the optional was empty, or like the underlying vectors. And then we just call for each to like remove each email from the subscriber list. And since option is now range, you don't even need to use like the member function transform. You can use pipelines all the way through, right? So we look up the user, transform that into emails, right? Because it's now a range of 0, 1. So I transform it, which invokes the function on each element, of which we have at most 1. And then we've got a range of range, and so we join it to flatten it and use that in a for loop. And this pattern of transform and join, we've seen that, right? We transform the thing, and then we want to flatten it out, right? This is the end-then member function of optional. There isn't yet like a range adapter that does like the end-then equivalent for optional, right? Which takes a function that it takes each element of a range and maps that to a range, right? And then we want to flatten all of those ranges back together. But there might be one in the future. There's a proposal to add transform join. It should really be called end-then, right? Because it is the end-then equivalent. And this does a transform and a join by like applying a function that returns a range to each element of our thing. And then we can just pass that into the for each. Questions about that?
When I've played around with things like pipelines in the past, the main issue that I have is debugging.
Right.
Like debugging even multiple nested
Right.
is trivial.
Right.
And what are your advice for debugging and digging into each individual piece, saying which returns optional, which returns values?
Yeah. It's a bit clunky because this is again like the CPU is imperative, the debugger expects imperative code. This is a different pattern. This is the mismatch. This is a fundamental problem. It's just annoying. Like there isn't a lot you can expect like doing like the convenient ways to like print intermediate steps of the pipeline to see where you went wrong, right? But usually because like you can assume that like each view is correct, right? And then you have to just have to think where's the bug in my lambdas that I passed the other thing. So there's a lot less surface area. Whereas if you have the multiple nested for loops, like you could have a bug in the for loop, like you increment the wrong variable in one of those things, right? And you don't have to worry about this sort of, so the surface area of bugs is simpler, which. But then exchange debugging is harder, right? It's a trade-off. Right? Yes?
So in this example, we're looking up an ID maybe in a database and we're trying to send an email. It's great for the, the ID doesn't exist in the database, but what if the database is missing and you need to handle some kind of error? What do you recommend there?
So what if the lookup user can fail because the database doesn't exist?
I'll take my $5 later.
Yeah. Right, it might throw an exception, and in this case, right, it's not critical. We just log the error and retry later when the database is available. And in order to compose that in a functional way, we need to deal with values. Right? We cannot really compose exceptions because exceptions aren't values. Right? Composition requires values. So let's model it instead of using exceptions. Let's use expected. Right? So let's say lookup user returns either user or DB error in form of expected. So expected TE either contains a T, which is the value, or E, which is an error. Right? So we either get a user or we get an error. And then we can write code using like if statements. Right? So we look up the user. If you have a user, we remove its email from the subscriber list. Otherwise, we log the error and retry later. And now we have a composition chain. Right? We start with the user ID. We map that to a user or DB error. And then we map that to an email or DB error. But of course, this is again a bit clunky. And you probably know what's coming. Right? We want to get an expected user to an expected email using a function that maps a user to an email. Luckily, there's transform, right? So transform takes a t, maps it to a u, right? And then we wrap that into our expected. So if we have a value, we transform the thing. Otherwise, we leave the error unchanged. And then we can write code like this. So we look up the user, we transform that into an email, and the final transform is the action. And expected actually supports void, right? So we don't have to deal with monostate, right? We can just transform, give me the action to remove the thing. And again, this will only do something if the lookup user didn't fail. And then we handle the failure, right? So if we have a failure, we log an error and retry later. And of course, we can also turn this final thing into an action, right? Because we really want to do something when we have an error, like on the error part, not on the value. So for that, we've got transform error. So transform error is just like transform, but instead of getting the value, it gets the error. So if we have a value, we don't do anything and just wrap it through. Otherwise, we invoke the function to transform the error. And now we can replace the final if by putting a transform error at the end. So transform error gets our error, right? It's only invoked if we actually have an error in there. We log it and then retry later. And expected does not support void in the error case, but this is actually a good thing because it would allow us to silently swallow an error. In this case, we actually don't care about the error anymore, so we can explicitly swallow it, right? By using like monostate to say, hey, we dealt with the error in the appropriate way. And now we sort of see the declarative thing in action, because there is the temporal dependency between those isn't like entirely clear. Like we either invoke the first two transform or we invoke the last one, but we never invoke all of them, right? Because that would be. Right? So we just declaratively say what we want to, how we transform the values and how we want to transform the errors. Well, what if the query email needs another database access and that can also fail, right? And then we deal with expected again and require two if statements. And I guess you can see what's coming now, right? We've got end for that. First we've got join, right? To flatten the thing. Just like before, turns an expected into an expected. But really we want end then, right? And then takes a function that turns a t and returns an expected, right? So here, the function itself can fail that we transform. And then we don't turn an expected of an expected, so we don't wrap the thing in another expected, but we just invoke the function and return that as the result. Otherwise, we forward the error. So now we just use end then to get the email instead of transform. And again, it's really obvious which parts can fail, right? Only the ones with end then can in turn cause more errors. And the transform parts don't, right? So you can just look at it and see which operations can fail. Like this is one advantage over exceptions, where it isn't obvious which one can fail. Now, one downside of using expected for this is that expected requires the same error type the entire way through. So if we want to first query a string and then pass that string into an int, using like which can result in different errors, then we cannot just use end then to compose them, right? Because like, what's the error type? Well, the error type is like either db error or pass error, right? But sadly, end then doesn't compile, right? And then requires that the expected and the expected function are the same error type, or like at least convertible. So what we would need is like to eagerly turn that into the appropriate expected, and this is just ugly, right? This is really something where like we would need some better technology. So if we really wanted something like an expected that takes a t and like multiple errors, right? And then when you call end then, it will just accumulate the different errors in a nice way and automatically handles that. And so by using optional and expected, if you use those to model optional and fallible results, we have very convenient compositions, right? We can call transform to produce a new value in a way that cannot fail, right? And transform error to handle errors. And then we have end then to compose it in a new way that can fail. Right? So if we introduce new errors, we use end then, and this will then merge all the errors together in a nice way. Unfortunately, if you have like different kinds of failure or optionalness, like the merging isn't quite nice, right? Because the cursor can't easily mix like an optional and an expected, right? Even though like logically an optional is like an expected of a t and a void, right? Where we don't have an error, but like the standard isn't entirely up to date for that. And so by using transform and then, we don't need to use if. Right? No if statements in our code. We just write our pipeline, and then when we execute the pipeline, the ifs are hidden in the compositions. Okay. So based on the time, I'm just going to go to the last session, and then we can go to questions later. So let's look at the final thing, composing I/O. So in a pure functional programming language, all functions are pure. This means they are mathematical functions. They cannot do any side effects during computation, so it doesn't matter whether you call it 0 or 1 or 2 times, and always results in the same value when called with the same input, just like a mathematical function. This means that you cannot have any global variables that you can manipulate with your functions, and you also cannot do any I/O or interaction with the outside world, right? Because a function like readInt returns a different value every time you call it, right? This is not a pure function. So how do functional programs actually do anything? Right? If you can't interact with the outside world, you can't do anything, right? You have a nice program, but it cannot take any inputs and it cannot write any outputs. So it doesn't matter whether you run it or not, since you can't, it can't do anything. Right? How will you write a function like this that reads an int and writes this int squared back to the output? Well, they cheat a bit. The idea here is you manipulate actions. So instead of having a function readInt that returns an int, you have a function that returns an action that will return int. And now this is a pure function, because it will always return the same action, the action that reads an int. Executing the action is non-pure, but we don't need to worry about executing the action. Right? The function itself is pure. And similarly, a function called writeInt, right, returns an action that will write the int. And again, this is a pure function, because it will always return the same action. And actually running it is non-pure, but let's not worry about that. And so, of course, you can't directly just get our int and square it, right? Because when we call readInt, we don't get an int. We get an action that computes an int. So this code doesn't work. But what we instead is like a function that turns the int we just read into its square value. So we want to turn an action that reads an int into an action that reads an int and square it. We want to sort of transform the value using transform, right? So we can imagine that the actions provide transform and end then, right? So if you call transform, you give it a function. This function will be invoked with the value and returns a new value. And again, this is pure, right? We just create a new action that is composed of 2 other actions. And then we compose it with another action, and this time we don't use and then, otherwise we would have an action of an action, right? So we flatten it out and use and then because we want the flattened thing, right? And so after we've computed the square int, we call and then to write it out, to get the thing. And now we've got a pipeline. And everything so far is pure, we just composed some actions, right? And when executing those actions, they will read an int, pass that int to the lambda of transform, which will return a square value, pass that to the writeInt function, which will write it out, and then flatten it out. And so the only thing that actually impure is our main function, which calls it and runs it. Right? This is the non-pure statement. And so what functional programming languages do is they pretend the main function doesn't exist. Right? Their main function actually returns a list of actions, and then something else is executing those actions. And the something else part isn't pure, but that's fine, it's the runtime. You have written a pure program. The actual execution happens afterwards. So when you write something like Haskell, essentially, all your entire execution happens after your Haskell program is done. Because all the Haskell program does, it composes the actions, and then they're executed afterwards by the runtime. And that way they sort of trick the thing around. Now, of course, here in C++, we don't need to be pure, right? Our functions have side effects. But it's still a good idea to separate the I/O from computation, right? So you just have one function that takes the input, produces the output, and doesn't do any I/O itself, right? This makes it much easier to test, because you don't have to test your I/O. It's much easier to use swap different input or output procedures. So it's still a good idea to separate I/O from computation, even though you're not necessarily required to. And this pattern of composing actions can still be useful. Right? The idea is we declaratively compose actions and then execute them later. So in C++26, we will have senders receivers, which allow us the way to do multi-threaded programming. And they're built about this idea of composing actions. So we have our function that does something. It takes a scheduler. And using a scheduler, we can execute work on a thread pool. What's the work that we want to execute? Well, the first thing is we want to start a pipeline on the scheduler, which computes the 10th Fibonacci number and prints it out. Right? And so here we get the schedule call returns you an action that will just run on the particular schedule. And then we transform it. For some reason, the transform in senders receivers is called then. Right? It's a bit confusing, but this is a transform. It takes our action and transforms it into a different action. Right? In this case, schedule doesn't give you any values, so the lambda doesn't take any values either. And it just means that after we're done with the first action, which means just start work on a thread pool, right? we will transform it to do something on this thread pool. So the first lambda will execute on the thread pool. And similarly, we do another thing, schedule it, and this does a prime number check. And this will also execute on the thread pool. And crucially, because we're just composing actions, we haven't actually done anything yet. Right? We just described our pipeline. And then we want to wait until both of those are done. Right? So we call when all, which is another thing that takes like multiple actions and returns the action that is only done when all of the intermediate actions are done. Right? And we could like imagine chaining more work in that. So we could say like when all, then do something else, and so on, and sort of compose our actions as much as we want to. Right? And then the sync wait call is actually the one thing. Right? So at this point, we actually run the actions which will execute in parallel on the thread pool, right? And we block until we're done. Right? So the first lines just declaratively compose a pipeline, and then we execute that in parallel. And this is like the real power of like doing this declarative thing, right? Because we can very easily parallelize our code, right? We could imagine that we put like our ranges pipelines in there, and stuff like that. This makes it like very easy to write parallel code without having to write any threads yourself, right? And you don't have to deal with any shared state and so on. It's really nice. So the general takeaway here is declaratively build your plans, then execute them later, and separate I/O from computation. And that way, you minimize impure functions, which means your code is nicer to test, nicer to reason about. It's not like any function can do anything, right? It's more isolated. So you might have noticed that this seemed all a bit repetitive. We've got a range which contains 0 or more values. We can transform those ranges to change those. Right? We can call transform join to like change each value to like a range of values and then flatten them out in a big range. Or we call join to flatten a nested range of ranges. When we for optional or expected, they have a value or nothing or some kind of error, right? We can transform to change those errors. We can call and then to like change the value using another function that can in turn fail, right? And sort of flatten a nested optional by doing the transformation. And we can write the join function that just does the flatten for us. And then we see those I/O actions, right? They contain a value in the future, so to speak, right? It's an action that will do something with value, but only when we execute it. So it's a value in the future, right? We can use transform to change those values. Right? And so when we have a value, we call transform to change those. And we call and then to compose it with another action, right? And we can also imagine a function that joins, that like flattens a nested action, right? And like, those are all kind of the same thing, right? And this is because they are all monads. Right? Each one of those is a monad. And like, people say like monad is this incredibly complicated thing, but like, it's not really, right? Like a monad is just something that has a transform and then and a join, right? And then you need something to like put a value in there, and like there is some relationship between transform and then, right? But you can figure that out. Like and then is just transform and join, and for example. And so when you implement it, you need to respect that. But that's all there is to a monad. Right? And monads are incredibly useful to functional programming because functional programming is about composition, and monads are what enables composition, right? Because those are the functions you need to compose. Right? This is what functional programming is about, and this is why monads are so important. Right? They allow you to compose errors, they allow you to do I/O, right? Because I/O composition is just a monad, right? And this is the essence of functional programming. Okay. Thank you very much. I work at ThinkCell. We are hiring. I have our L value, R value socks. So if you want those, come by after the talk. Are there any questions? You know, for microphone. Sorry, if you.
I noticed you did not mention or else. Does that just turn out to be redundant with the other three?
Yeah, so or else is a convenience function on optional and expected that essentially unwraps the thing. So when you want to get out of it, so like value or turns an optional t into backender and or else is something like this. So you want to leave the pipeline. You can call or else. It just didn't fit in the. Yeah, it's useful, but just.
Hi, great talk. So I know that GCC supports an optimization. If you said O level 3, you can do recursive functions, and then it will automatically convert it into a for loop for you.
Right.
Would that work with the example where you had a Fibonacci sequence and with the yield?
No, because this is a like tail call optimization, It only works if you have a single function call at the end. And with the Fibonacci, we have 2. So the best it could do is could turn 1 into a loop, but then it's a loop still with a recursive call. Because fundamentally, the recursive call thing has like exponential runtime, and the optimization can turn that into linear runtime.
Thanks.
Yeah. Thank you for a super clear talk. Is there an easy way to reason about whether these views and pipelines are going to do things like allocate memory or lock mutexes?
Yeah, so they don't.
Cool. Thank you.
Like, they don't allocate memory, they don't allocate, at least, yeah, like we haven't standardized. Like some algorithms allocate memory, right? But like the pipelines don't. Unless you have like a function in the transform that allocates memory, stuff like that. Okay, thank you. Please come by and get the socks.